In this segment, we'll talk about how to integrate a function so that we can find the location of a body when the velocity is given to us. Two important factors which will be covered in this particular example would be how to use the integration by parts as well as using the fundamental theorem of calculus. So here is the problem statement. We're given the velocity profile given by this particular expression here. V is the velocity, t is the time. We are told that at time t equal to 1 second, the body location is 7 meters. We want to find out what the location of the body will be at 2 seconds and what the location of the body will be at 0 seconds. So if we look at from drawing a sketch here, at t equal to 1, we know what x equal to 7, x is equal to 7. But what we want to find for part A is, hey, what is the value of x at t equal to 2? And for part B, we want to be able to find out, hey, what is the value of x at t equal to 0? So if we look at the fundamental theorem of calculus, that means that, hey, if dx by dt is equal to v, because velocity is the rate of change of location with respect to time, then from here, if we apply the fundamental theorem of calculus, we'll find out that, hey, if we want to find x2 minus x1, that'll be nothing but integrating this expression here, v sub t dt, from 1 to 2. Since we know what the location at x of 1 is, we can find out what the location of the body is at x of 2. Same here, if we look at this part right here, we can say that, hey, x of 1 minus x of 0 will be equal to integrating from 0 to 1 the velocity expression, again applying the fundamental theorem of calculus. And then since we know x of 1, we can find x of 0. So that's all there is to it. So what we'll have to do is look at part A and look at part B and find out what our answer is. So if you look at this one, we're saying that, hey, x2 minus x1 is equal to the integral of the velocity from 1 to 2. And this is part A we're talking about. So let's go and find out what the integral going from 1 to 2 v sub t dt is, since the velocity profile is given to us. So in this case, what we have is that the velocity profile is 2t e to the power minus t dt, right? Now we can see that, hey, maybe this can be done by integration by parts. What integration by parts is that, hey, this is the formula that u dv, integral u dv, is uv minus the integral of v du plus c. So let's see what u and v can be. So in this case, what we'll do is we will put v as minus e to the power minus t. Why? Because we know that dv will be equal to minus 1, which is this part right here, minus 1, because when we differentiate this one here, will be minus 1 e to the power minus t, will be e to the power minus t. So we can see that here we can replace, it will be dt here and dt here. So we can see that we can replace this part right here by dv. And that's how we're going to go doing that. And of course, the u part will be 2 times t. So what we're basically saying that, hey, we are going to rewrite our 1 to 2, 2t e to the power minus t dt as integral going from 1 to 2. U is 2t, so let's put that in parentheses. And we have d of minus e to the power minus t, we'll put it there. So if you go ahead and look at this, it's the same as this one right here. But what we have done is that we have broken it down into u dv part right here. So that's for u and this is for v. Now we can apply the formula to be able to find out what the value of the integral will be. So what we have is the integral of 1 to 2, 2t d minus e to the power minus t. And as we said that this is our v and this is our u. So this is our u, this is our v. So that'll be u times v, which will be 2t times e to the power minus t, and the limits of this will be from 1 to 2, minus v du. So v is minus e to the power minus t, and the derivative of u, which is 2t right here. So that's 1 to 2. So what that gives me is that this is minus here, because that's the value of v. So we have minus 2t e to the power minus t going from 1 to 2 minus 1 to 2 minus e to the power minus t times 2 dt here when we take the differential of this. So now what we can do is we can say, hey, this is minus 2t e to the power minus t from 1 to 2 minus. And now if we look at this one, we get 2, let's do plus, let's do 1, if we integrate this one right here, we minus e to the power minus t divided by minus 1 times 2 from 1 to 2, because 2 is constant, so we don't need to worry about that one. We could have taken that outside, but the integral of minus e to the power minus t will be minus e to the power minus t divided by minus 1 here. That just coming from that d by dt of e to the power at is a e to the power. So this is coming from the fact that if we take the derivative of e to the power at, it is nothing but a e to the power at. So that's where we're getting this from when we integrate this function, right? Integrate e to the power minus t there. So once we have that, let's see whether we can simplify it any further. Minus 2 e to the power minus t going from 1 to 2 minus, and then we have 2 here, right? This is minus, minus is plus, so it'll be 2 e to the power minus t here going from 1 to 2. So that's what we have there as the expression. Let's go and put the values of 1 and 2 as the upper and lower limit, and we'll be able to get an expression for it. So if we do that, we get minus 2 times 2 e to the power minus 2, then minus 2, then 1 e to the power minus 1. That's from the first expression. And from the next expression, we get minus e to the power minus 2, 2 divided by minus 1, minus e to the power minus 1 minus here times 2 divided by minus 1. And so from there we'll get, if we write in a simple form, we get this from the first one, and from the second one we get this. And once we have that, if we combine the e to the power minus 2 and e to the power minus 1 terms, we get minus 6 e to the power minus 2 plus 4 e to the power minus 1. If we put it in a calculator with 4 significant digits, that's what we're going to get as our answer. But keep in mind, this is x2 minus x of 1 is 0.6595, because we integrated from 1 to 2. So it will give us the difference between the location of the body at 2 seconds and 1 second. But we know that this is 7. So x of 2 will be equal to 0.6595 plus 7, and that gives us 7.6595 meters. And that's part A. So this is the value of part A. Let's go and see what part B gives us. So in part B, we had that x of 1 minus x of 0 would be the value of the integral going from 0 to 1 of the velocity expression. So since we now have, let's look at what 0 to 1 v sub t dt will be. That will be 0 to 1, 2t e to the power minus t dt going from 0 to 1. We can follow this exactly the same methodology as we did in part A, so we don't need to repeat it here because the way we're doing the integration is exactly the same. The only thing is that the lower limit is 0, upper limit is 1, rather than lower limit being 1 and upper limit being 2. So this one, without any extra calculations, this is what we're going to get, and this will be 0.5284. However, we know that, hey, we are given x of 1 minus x of 0 is equal to 0.5284. And we are given that, hey, this number is 7, that the location of the body at t equal to 1 second is 7. So what will be x of 0? So we'll have minus x of 0 will be equal to 0.5284 minus 7. Take 7 to the right side. So we get minus x of 0 is equal, negative x of 0 is equal to minus 6.4716. And that gives us the x of 0, that the location at 0 seconds is 6.4716 meters. So that's part B. And so now you have the location at 0 seconds, you have the location at 2 seconds, and you are able to answer this question. So we have used two main concepts in this particular example. One is using the fundamental theorem of calculus, and the second one is using integration of parts, then knowing what the integral of e to the power minus t is and what the derivative of t is. Once we have known that, that's how we're going to solve the problem. And that's the end of this segment.